Hi everyone. Can you hear me okay with this mic? So I'm a PhD student from Cambridge. Today I'm also talking on climate impacts, but for future volcanic eruptions. So my title is Climate Projections Underestimate Future Volcanic Forcing and its Climatic Effects. So this is basically the conclusion, and I'm going to talk you through how we reached this conclusion in this presentation. Okay. So first of all, let me give you a brief overview of the climate impacts of volcanic eruptions, since we have a diverse audience in this room. So explosive volcanic eruptions can inject sulfur dioxide into the stratosphere, which can form volcanic sulfate aerosols. These aerosols, if they're injected into the stratosphere, they can stay there for years, like 1 to 2 years, and affect our climate. But if they're injected to the troposphere, where we have weather, they can be like scavenged by rain, by wet deposition very quickly, and they only have a lifetime in weeks. So for climate relevant eruptions, we are interested in explosive eruptions that can inject sulfur dioxide into the stratosphere. Although we know that lucky may have climate impacts, but here we are focusing on the explosive volcanic eruptions only. So this volcanic sulfate aerosol can scatter incoming solar radiation, which then cause global surface cooling. And then they can also absorb long-wave and short-wave radiation in the stratosphere and causes stratospheric warming. So this stratospheric warming and global surface cooling effects in turn leads to other climate impacts, such as sea ice extent, ocean current changes, and dynamical changes in the atmosphere. So in the future, how do we even know when will the eruptions happen, and what do we know about the climate impacts? So well, to begin with, I will first talk about how the eruptions are represented in the current climate projection studies as in IPCC, the Intergovernmental Panel on Climate Change. If you don't know this name, this is the report that tells us we should keep the warming below 1.5 degrees Celsius or 2 degrees Celsius. So sorry for the shifting of the title. So to know about what happens in the future, we have to look into the past. So this figure shows you the explosive volcanic eruptions in the past 11,500 years from ice core and satellite records. So thanks to all the ice core and satellite groups, we can have a nice figure showing the eruption time series of all explosive eruptions in the past 11,500 years. So the color here shows you the SO2 emission. For the brown colors, it's all below 1 teragram of SO2. For the blue colors, it's greater than 1 teragram of SO2. You can see that the x-axis here is the years from present. We only have the brown circles in recent years. That's since 1979 when we have satellite observations. Before that, we rely on ice core record to know when the eruption occurs. And we pretty much don't know much about what are the exact volcanoes that causes these eruptions as represented by the triangles. So these are the eruptions that are not attributed to a certain volcano. So in current climate model projection studies, they actually only consider the period from 1850 to 2014 when they consider the future volcanic forcing. So they basically use a constant forcing derived from the eruptions occurred in this period of time. So you may immediately notice that there are actually no smaller eruptions in the ice core record from 1850 to 1978. And then there are much larger eruptions in the past 11,500 years than this period of time, like Tambora, some others, crater-like eruptions, etc. So how much bias is this current approach in the climate modeling studies? So to understand that, we generated 1,000 future stochastic eruption scenarios by resampling the record that I just showed you. So on the left figure here, this is one of the scenarios that we have generated because I have 1,000, so I'm only showing you one here. So this is the eruption time series of the future from 2015 to 2100. So the circles here all represented volcanic eruptions that I've resampled from the historical record. So we ranked these scenarios according to the annual SO2 flux. As shown in the red line here, this is the cumulative probability versus the annual SO2 flux of these scenarios. The blue dotted line here shows you the forcing level, like the volcanic sulfur flux used in the current climate projection studies. What we found is that future volcanic flux, first of all, is highly variable. It can vary from 0.5 to 6 teragram of SO2 flux per year. and that there is a 95% probability that this future volcanic flux actually exceeds the flux used in the current climate projection studies. So the question here is that do these biases means that the IPCC projections actually misrepresent the climate impacts of these future volcanic eruptions? So to answer the questions, so we selected some scenarios that we've generated and put it into a Earth system model called UKESM. So we selected 3 scenarios actually. We selected the scenarios at the 2.5, 50th, and 98th percentile of these 1,000 scenarios to examine the uncertainty of volcanic forcing in the future. And then we put it in a modeling framework called UKESM VPlume. So we developed this modeling framework by coupling an Earth system model, UKESM, with one-dimensional plume model, Plumeria. So what these frameworks do is that for each eruption that we input in the future, the plume model can actually calculate the plume height for the SO2 injection during the eruption, so that the plume height is actually consistent with the climate condition. And the figure here is just showing you a diagram to what is actually what a Earth system model is actually looks like. So it's basically dividing the Earth into small grids and has an atmosphere model, ocean model, sea ice model, and a land surface model, so that we can examine the climate impacts of volcanic eruptions on all these different models and outputs. And actually, we have completed over 4,000 model years, and it took in total a whole year to run all these model simulations. And I'm glad to tell you that it's done. So for the results here, first of all, I'm showing you only the important figures because there are so many outputs from the models. So I'm showing you here the global mean stratospheric aerosol optical depth. The stratospheric aerosol optical depth is actually a measure of how opaque the atmosphere is. Like if it is a stratospheric aerosol optical depth, it means that it's only considering the aerosol column in the stratosphere. So if it is higher, it means that there are more aerosols in the column. So we found that CMIP6, meaning the current climate projection studies, actually underestimates the future volcanic superflux and consequently the future volcanic forcing. If we use a stochastic volcanic scenario, we have sporadic forcing, like the figure here shows you. Well, if we use a constant forcing, it's basically a constant yellow line here that you can barely see. If we calculate the time averaged SAOD for a median future scenario, at the 50th percentile is actually 0.025, and this value is doubled than that used in the current climate projection studies. And I also calculated the relative volcanic effects on the large-scale climate indicators, such as the global mean surface temperature, global ocean heat content, sea level rise, precipitation, etc. So yeah, there are many terabytes of data going into this figure. And the main point that I'm going to tell you is that our stochastic scenario greatly enhanced the variability of all these large-scale climate indicators. So the light blue bar here shows you the contribution for small magnitude eruptions only. The navy blue bar here shows you the contribution from a median future scenario. The gray error bar shows you the error for 2.5 percentile to 98th percentile. So comparing to a scenario without volcanic eruptions, the volcanic effects can range up to 18%, for instance, for the global precipitation flux, and on average about 3 to 4% at least. And from this figure, we can see that small magnitude eruptions actually contribute to at least 30 to 50% of the volcanic effects on almost all the climate indicators, showing that small magnitude eruptions are actually climate relevant and they're important to be considered in the future climate model studies. In addition, if we compare the yellow bar here, which is effects of the current climate model studies, to the blue bar here, we can see that actually the current climate projection studies are estimating the future climate effects. Like the yellow bar is almost equivalent to the 2.5 percentile of our scenario, showing that it's actually similar to the volcanic forcing. The current climate model studies also underestimate the climate impacts of future volcanic eruptions. So, okay, take-home messages. So there are a lot of information going on in this presentation, but to summarize in one sentence, our simulation shows that current climate studies very likely underestimate the future volcanic superflux, consequently the volcanic forcing and the future volcanic effects on climate. And the contribution from the volcanology community in building the ice-score and satellite records is really important for us to understand the climate impacts of future eruptions. And that our findings actually inform the future climate projection studies in the next phase of the climate experiments to inform the IPCC. It should improve the magnitude and the representation of volcanic forcing in models. So that's all for my presentation. Thank you for listening. In preparation.